Okay, so in this video, we're pretty much going over energy, like potential energy and kinetic energy. So our first question, it's basically, like a divot, and it's going here, and then it's bouncing off the spring, and it's coming back up. And our question is to find the K, which is the spring force constant, right? So we're trying to find K. That's what we are looking for. So what we can set up is our potential energy initial is going to equal our potential energy final plus friction, right? Those two are going to equate each other. So what is PE? Well, it's mgh is equal to potential energy final. Well, this is the equation that involves spring force here. So it's going to be 1/2 kx squared, and then plus friction. Well, what is friction? It's mu mg, right? And then we have to multiply it by the distance that it travels. So what we can do here, we can set this all up. So mgh, what is m? 25.0, g 9.81, h given 8.55 is equal to 1/2. What we're solving for, k, x is given, which is 2.5 squared, plus mu, which is 0.125, times mg, which is 25, times 9.81, and then that is times, sorry, we'll go at the bottom here, but this is continuation. Well, this is 13.66, right? But it is traveling this distance as well. It's going into the spring a certain amount of distance, so you have to add these two distances together. So you get 13.66 plus 2.5. So now if we go into our numeric solver, we just plug all this long equation in, and we can get our K, which is going to equate to 512, and then units is Newton per meter. So that is how to solve one of those questions. Okay, the next question regarding it is how high can it bounce back after it is, pushed into the spring? How far is it gonna go up here? So what we can do is we can use this equation here. By the way, for the last one, it was the potential energy of the spring force, but now we can use the final, which is going to also be mgh, right? So we know friction and we know potential energy initial, and now we are just solving for this h right here. So we can go PE initial, which is 8.55 times 25 times 9.81, mgh equals our friction, 0.125 times 25 times 9.81, and it's times 2, right? And times 13.66 plus 2.50, right? That's our friction, and then it is plus 25 times 9.81, right? mg, and then our height final. And we can use numeric solver, right? And our height final comes out to 4.51 meters. And that is how to find the height. This 2 right here is to indicate that it goes forward, right? It travels that distance once, and then in the spring, it bounces back, and it goes that same amount of distance is what it travels inside that friction right here. But after that, it passes frictionless. So that's the whole point of the 2, because it goes through it twice, if that makes sense. Okay, our next question is similar, but instead of like a slope here or like a curve, it is a straight line, and there is a theta given. So this is pretty much, we do the same process. By the way, we're finding x here, the spring distance that it travels, right? The process is pretty much the same, but our normal force is going to be different on this friction here because it is, on an incline. So the normal force is going to, mg cos theta, right? So we can set this up. So our potential energy, which is mgh, right? 30.0 times 9.81 times 9.00 equals friction, which is 0.255, times our mg 0.81, and right, it's cosine 43.5, because that is, how the normal force is, how on an inclined plane. And then it is multiplied by the distance, right? 4.15. then it is going to be, you have to add the spring force, pretty much, the spring force potential energy, which is 1/2, right, kx squared. We know k, which is 765, and x squared. So that is the long equation that you set up, and you just, once again, use numeric solver, and your answer should come out to x equals 2.52 meters. And so it's really similar, not too bad. You're just kind of combining topics here: spring force, inclined plane, and then these powers and energies and stuff. So yeah, not too bad. Okay, our next question asks, will this object make it over this ramp right here, or this little incline, or whatever you want to call it? So the height is 4.93 meters, right? The mass is 14.1 kilograms, and it's going to go through this system here, and we're seeing if this will overcome it. So how do we set this up? Well, we have to pretty much, there's no really variable here what we're using. We're just looking at this and what Mr. Nutter calls piecemealing it. So we can set this up into small little things. So at first, our potential energy here, which is going to be our potential energy initial, is going to equal mgh, which is 14.1, 9.81 times 4.93. And let's do that. 14.1 times 9.81 times 4.93. We get 682 joules, right? That is our potential energy, and that's what we're starting with, right? And now we have to figure out if the frictional force, right, is, and the potential energy at the top is going to be greater than or less than this number. If it's greater than, then the two energies combined, if the friction and potential at the top are greater than this number, then that means it cannot overcome this little hump right here. But if they're less than, then that means there is enough potential energy to overcome this hump right here. So let's figure that out. So the potential energy at this, what we can call this potential energy at x, and this distance, this star here is x, is going to be 14.1, 9.81, and the height is 4.25. So 14.1 times 9.81 times 4.25, we get 588 joules. Forget that. So already we have a high amount of joules, so we have to know if the friction force is going to be, large or not. So how do we find friction? The frictional force energy is going to be mu mg, right, distance, and then it's going to be cos theta, right, because it is on an incline right here, with this theta being theta that we use. Or distance multiplied, then it doesn't really matter, it's commutative. So we can do 0.680 times 14.1 times 9.81 times the distance times cosine of 64.5. So we get cosine 64.5. And this whole frictional force comes out to 184 joules. So now let's add these two joules together. So 588 plus 184. Is this going to be greater than or less than 612? Let's find out. Well, you should be able to know this. Plus 184, and it is 772 joules. So 772 joules are required to make it to the top of this vertex right here. However, the potential energy that we're given is 612 joules. So thus we can conclude that there is not enough energy to make it up this hump right here. So it will actually end up somewhere on this inclined plane.